Okay, so I got started without thinking about starting the recording, so just talk through this really quick. The first one, you're using the chain rule. And the main thing to note is that you know the derivative of arctangent is 1 over 1 plus x squared, so this becomes 1 over 1 plus r, the fourth root of r squared. And then you have to multiply by the derivative of that fourth root of r, and I've done that right here. And there you have it. For this one, we have a product rule. And so I've broken this down. The derivative of 2 to the x is, here, I'll just jot this down up here just to remind you. The derivative of 2 to the x is the natural log of 2 times 2 to the x. It's just like e to the x, only we have this natural log that you have to, sort of a correction factor. At any rate, so here we're going to just do the fg prime negative cosecant times cotangent, and then plus f prime times g. So let's see, can I make this 6 ln of 2 times x times 2 to the 3x squared cosecant x. How's that? And since I don't have to simplify it, I'm just going to box it up and say I'm done. I'll put a little bubble around that. Okay, the next one, this is a quotient rule. And so low d high minus high d low over low low. So I'm just going to do it using that sort of mantra. So we have g prime is low d high minus high d low all over low low so let's see, low d high, high d low over low low. Put that in quotes. That's my little thing. Anyway, there's my derivative. Final one here. We have to remember, let's see, let's just go over here. The derivative of the log base 10 of x is equal to 1 over x times the natural log of 10. So we have that same deal that you have this correction factor that we have to make. So here we'll just put that in a little cloud. Something to remember. So we're going to be using, what, the product rule and the chain rule? My goodness. Product rule. And then here, chain rule. So it's probably best if we sort things out, but I'm not going to. Let's see. Let's use the same form up here. I did the derivative. The first thing times the derivative of the second thing. So this chain rule, I've got this derivative of the log base 10. And then I have to multiply by the derivative of the argument there. Okay, so that's the first part of this product rule. And then we need the second part. Should be a little easier though. So let's see, plus 2/3 secant squared. So it's just secant squared, derivative of tangent is secant squared. Times the log base 10. We're going to leave this thing alone. That's it. I'll just leave it. Beautiful. Okay, so what about this sort of thing? Anytime you have a function to another function sort of deal, you're going to have to use logarithmic differentiation. So the way this works is you do the natural log of y, I guess, is equal to the natural log of the cosine of x to the square root of x. And then we're going to use the rules of logarithms, which say that I can take that radical x and put it out front. And now I can just use the product rule on that. So let's see, this is going to be 1 over y times y prime. Excuse me. So this will be 1 over cosine of x times the derivative of cosine x, which is negative sine of x. Let's see, plus, so product rule, 1/2 x to the negative 1/2, natural log of cosine. Things are tilting slightly. Let's see if I can right them. I've righted the ship, but one thing didn't get, there we go. Okay, all that's left is to multiply both sides by y. And when I do that, so here, I guess I'll just copy, since I can. So it's all of that stuff times y. And so now I just have to rewrite it one more time, which I know it's a bit of a pain, and change that y to the appropriate function, which is cosine of x to the square root of x. Wow, that's a messy thing. I'm sure it could be simplified a little bit, but let's not go there. Let's just leave it the way it is. Okay, it says the tangent line to y equals f of x at a particular point is this sort of thing. I want to know the slope of the tangent line to this. So essentially we're doing f inverse prime evaluated at 6. Okay, so we need to remember that this is, let's see, 1 over f prime evaluated it at f inverse of x. This is just the standard formula for the inverse derivative. And just do it like that. You could get this a variety of ways. There's a sort of a shortcut, sort of cheater way of doing this particular problem, but let's see if we can do it using this. So let's see. I'll just, didn't mean to mark that up. It's going to just move all this over. Okay, so we want, so here's the formula. And so we have, so this will be f inverse prime evaluated at 6, will be 1 over f prime evaluated at f inverse of 6. Okay, so f inverse of 6, it says that, okay, so let's see if we can figure out what f of 6 is, or, well, here, f of 4. So f of 4 is going to equal the linearization, I guess, at 4, if you want to call it that, the line there. Because that's a tangent line, it should match up at the point. And that's equal to 12 minus 6. I better write this like this. 3 times 4 minus 6, which is equal to 6. That means that f inverse of 6 is going to equal 4. So, okay, so then that we're going to stick in here. Shouldn't this have a negative? I feel like this should have a negative. It should be a negative. We're going to put a negative there. Okay, so then f prime of 4 is the slope, which is equal to 3. So there it is. So the cheater way is to just recognize, first of all, that 6 and 4 are inverses, that f of 4 is 6. And then the slope at 4 is 3. And so the slope, when you do the inverse function, you'll end up having the slope will be perpendicular. So there it is. Is that right? Should it be negative 1/3? Should be positive 1/3. I'm going to have to do this from scratch. Okay, so let's go ahead and derive the function. So here's the formula, the derivative f prime of f inverse of x times f inverse prime is equal to 1. So that means that f inverse prime. Yeah, I had it right the first time. I just doubted myself. I think I was thinking of the whole perpendicular thing. That it's not perpendicular. It's just this. So I've got it all right here. Should be 1/3. All right, we're moving on. Let's go ahead and sketch something that matches these conditions. Second derivative is 0 for x equals 3 and x equals 7. Here, there's not a lot of guidance given. All you know is that this is going to be concave up in that range and concave down. There, here, let me just, I just thought better of this. Do this before I forget. Just put this in a little bubble. Okay, so concave up between 3 and 7, concave down less than 3, greater than 7. So let's see, it's got to be concave up between 3 and 7. Here's 3. Here's 7. Doesn't really matter. It doesn't have any other information. Many different possible answers to this. So let's just go ahead and try this. Oh, that was terrible. That was bad too. Let me do one more try. That was almost perfect. Okay, so we'll go with that one. And then we're supposed to be concave down from here on out. Delete. That's not bad. So I guess I could just slide things around until it looks good. There, that's concave down, isn't it? And let's duplicate this thing. Move it over. Come on. And I'll link things up here. There. That looks good. Let's see if I can just make this a little thicker. And then we'll be moving on to the next one. Come on. There we go. That looks pretty good. So just to be clear, this is concave down. This is concave up, concave down. All right, onward. Here we have a local min, and here, once again, both of these, there's a lot of variety. So many possible graphs. Here's one of them. Okay, local minimum at x equals, let's see, so this is continuous, this is continuous. I should have probably said that this was also differentiable, but well, local minimum at x equals 1. So let's start putting points down. There's going to be x equals 1. That'll be a local minimum. Local maximum, x equals -3. So x equals -3. Local maximum. Let's see, absolute minimum at x equals -5. So it's got to be below my other dot. So let's just put it down here somewhere. Absolute maximum of x equals 4. So it's got to be over here somewhere. And then in order to make that an absolute maximum, I got to do something like this. Now, honestly, it would work if I just connected the dots. I'm going to try to make it look a little prettier. That's not too bad. Okay, and then we'll get a few more of these just for fun. Let's see. I'll put those in just a sec. Fix that in a bit. Actually, I could probably just stick this one here. Let's see if I can move these dots around so that this looks good. Oops. Up a little bit higher. There. That looks pretty good there. Now I just need to somehow connect things up. You know what? I don't need these. I just realized. Delete that one. Delete this one. So this is just one, once again, this is a possible solution, but it is by no means the only possible solution. Not good enough. Okay, so here, let's just point out, this is a local max, local min, absolute max, and this one is an absolute min. So, yeah, here again, I'm just going to duplicate this, put it down here. I'll change color so it looks like I actually wrote it a second time, but I didn't. Okay, we're going to take a look at this function. I'm going to verify that the mean value theorem can be used on this function. What does that mean? We're going to check to see that this thing is continuous on -4 to 1, question mark. And the answer is yes. Okay, I don't need to write it all out. X equals 2 is a problem, but x equals 2 is not in the interval that we're interested in. So that's the first thing we're going to check. Number 2, we're going to check to see, is this differentiable? On -4, 1, question mark. That's also a yes. Once again, the only issue is going to be with x equals -2, or x equals +2, sorry, and that's not in our interval. And that's all we really need to check. And so now we're going to compute the average slope. The average slope is going to be f of 1 minus f of -4 over, so this is m average over 1 minus -4. Okay, so what is f of 1? F of 1 is -3. f of negative 4. Hey, is this really going to be that ugly? Yeah, I'm going to double check my math on a calculator. Yeah, that is negative 3, and then when I plug negative 4 in there, I'm going to get negative 2 over negative 6, which is 1/3. So minus 1/3. Okay, so negative 3 minus 1/3 is negative, let's see, 9 10/3. Okay, so that's going to end up being negative 2/3 when I get done dividing. And you're going to do that so that you can flip the bottom and multiply. Okay, now we need the derivative. So we're going to do the quotient rule again. So and as you can see, this thing does have a problem at x equals 2, but we don't care about x equals 2. Okay, so let's see. This ends up being, that's going to be negative 4 on top, and x minus 2 squared on bottom. So I would like this, so I'm going to solve this. Solve. Negative 4 over c minus 2 squared is equal to negative 2/3. So that's my job. That should be a c. So cross multiply. Let's see, divide both sides by negative 2. Then I could just do the square root of both sides. Don't forget plus or minus. Then we're going to get c is equal to 2 plus or minus the square root of 6. But bear in mind that not both of these are going to be in the interval that we're interested in. So we just need to select the correct one. Let's change colors. Oops. Change colors. Hold on a minute. There, just so that we can see. Good enough. Okay. So 2 plus radical 6 is definitely bigger than 1. Whereas 2 minus radical 6 is between 1 and negative 4. So, so the correct answer is 2 minus radical 6 for C. Okay, what are we doing here? I have a function. This is the derivative. That's the derivative of my function. I want to determine the location of all local extrema. Okay, so let's first of all find the critical values. Are at x equals negative 5, x equals negative 3, x equals negative 2, x equals 0, and x equals 6. So how did I choose all of those numbers? Well, those are the places where the derivative is either 0 or undefined. So maybe I should jot that down. These are where f prime of x is 0 or f prime of x is undefined. Okay, next. So those are the critical values. Now let's think in terms of the slope. So we're going to do this first derivative test. I guess I made my number line a little bit big. So when x is less than 5, you can see that f prime of x is positive, and here f prime of x is negative. Then f prime of x is positive. So what I'm talking about here is like, all along here, f prime of x is negative here. F prime of x is positive. Let's see, do I need to do maybe one more here? F prime, because remember, this is the graph of f prime of x. So where it's above the x-axis, it's positive. Below is negative. So f prime of x is negative. F prime of x is positive. F prime of x continues to be positive. So that means that where you change from negative to positive, that's going to be a local minimum. Sorry, positive to negative is a local maximum. X equals -5. So I'm looking for places where we are going from a positive to a negative. X equals -2. I think those are the only ones. And then local min. All right, x equals -3, and x equals 0. I guess I'll jot this down for anyone who doesn't want to listen. Local max is f prime of x changes from positive to negative. Local min, f prime of x changes from negative to positive. Done. I'll put that in a little thought bubble. Good enough. Determine the intervals on which the function f is concave down. F is concave down, so f, maybe I'll put down the rule first. F is concave down when f prime of x is decreasing, which would mean that f double prime of x is less than 0. That's what concave down means. So we're looking for places where this is decreasing. So this whole stretch, that's concave down, and this whole stretch is concave down. So it's over there. That's x is less than -4, and x looks like it's between 3 and 6. So if this is a particle, when is it slowing down? Slowing down means that, let's see, this is when so when it's slowing down, when f prime of x and f double prime of x have different signs. Okay, so it's either moving backwards and f double prime is accelerating in the forward direction or vice versa. So I guess I could make myself a little table here, and we'll have f prime and f double prime. So here we're going to put the important points. -5, -4, -3. So I'm going to put all the critical numbers and all the points of inflection. Okay, that's it. Okay, so f prime is easy. You can actually just read it off the graph. F prime is positive, and then it's negative, negative, positive, negative, and it's positive the rest of the time. So that's the actual function, because this is a graph of f prime. F double prime is the slope of this graph. So you have a negative slope, and you still have a negative slope until you get to the bottom of that minimum. And then you have a positive slope, positive, 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 negative, positive. Okay, so when is this thing slowing down? It's when there's a mismatch, different signs. And so it looks like that is going to be when x is less than -5, when x is between -4 and -3, when x is between -2 and 0, whoops, and then from 3 to 6. I'll put a box around all of that. I'll do this. Okay. All right, let's see if we can do this next one. We're going to have to use implicit differentiation to find the tangent line to this thing. So we need to get the slope first. So let's see. I'm going to just go ahead and do the derivative, a little bit of a chain rule. It's not much of one. 8y dy over dx is equal to 27y squared. So we're going to solve for dy over dx. A little bit of algebra. You can handle this. Let's see, 10x minus 2 over 8y minus 27y squared. Okay, now we're going to plug in the point. So dy over dx. When xy equals 3, 1. So plug 3 in there for x. It looks like we're going to get something ugly. 10/19. Okay, so there's my slope. I've got my point up there, 3 and 1. So that was, thankfully, it was given to us. So let's go ahead and do y minus 1 is equal to 10/19 x minus 3. And I think I'm just going to leave it like this. Onward, let's get a linearization, linear approximation. So L of x is going to equal f of a plus f prime of a, x minus a. So I guess I need f prime of x. Let's do that over here. 1 over 1 plus x squared times 2x. It's the chain rule. So let's see, f prime at 0 is actually 0. Well, this is boring. Man, that was not a good choice, was it? because check this out. F of 0 is also 0. So my linearization is 0 plus 0 times x minus 0. Well, that's easy enough. Well, here, let's just pretend that we were going to do this. This would be the natural log of 1 plus 0.01, which is the natural log of 1 plus 0.1 squared. Since I'm trying to match this function up here, so basically I'm plugging 0.1 into the function up there, and so I'm going to use the linearization, but not much going on here. Now, as far as it's underestimate or overestimate, bear in mind that what we're doing is we're using the tangent line to estimate my function. And so if your function is concave up at this point, this will be an underestimate. If, on the other hand, you have the point and it's concave down, you have an overestimate. So let's find out what we're dealing with here. Let's take the second derivative. Where's my, okay, let's see, f prime. So the second derivative, we're going to have to use the quotient rule. Low d high minus high d low over low low. So that's going to be 1 plus x squared minus 4x squared. 1 plus x, oh, sorry, square that. So let's check the second derivative at a at 0. It's going to be 1. So we got an underestimate of the true answer.